Welcome to Chapter 9. In this particular case, we're going to be talking about reducing the project duration, which is commonly referred to as project crashing. We're getting closer to the end, and this is the start of our final stretch for the course. Understand some of the reasons for crashing a project as one of the objectives. Look at different options for crashing a project when you have constraints, which you always do, and calculate an optimal point for at what point do does the crashing diminish in importance. To relate this to something you took in economics, you may remember diminishing marginal returns. Well, in this particular case, that's exactly what happens in project management. The costs of the first unit of crashing are the cheapest, and as you keep crashing the project more and more, or shortening the project more and more, the costs increase. So the slope is not linear, it curves upwards. So here are the 6 topics. It's shortening the duration of a project. It is not cost-benefit analysis. I've had this discussion with people who do not teach project management, and they think it's cost-benefit analysis. No, there is a cost and a cost only. The benefit is shorten the project duration. Now, there can also be a benefit if there's a fine for being late, but we don't deal with that in an introductory course. So some of the reasons: you need to get it to market quickly. There's been companies who literally missed their window of opportunity because they were, in some cases, trying to be too perfect, or some that weren't good enough, and they caused the company to go out of business. But getting the product to market on a certain length of time. You had unforeseen delays, so now you need to get caught up, just like you do in your own lives. You have bonuses for completing the project early, and overhead costs and pressure for in case the project runs late. And you need to also then assign these resources. Remember, those people, that equipment, those materials can be used elsewhere. And on an earlier chapter, I talked about the fact that they needed a project crashed, reduced, so they could tear down the parkade so they can construct a new building, because that would have delayed the start of that building and it would have delayed the completion of that building. So you can add resources, you can schedule overtime, things along that line. You can still do it quickly and correctly. There's certain things though that you can't really crash or can't crash very much, such as an example would be like heat treating. If you heat the metal to too high a temperature and try and heat treat it that way, it can make the metal very brittle. It needs to be, the temperature needs to increase at a certain level over a certain length of time. It needs to stay at that temperature for a certain length of time, and then it needs to cool. And an example in your own personal lives: cooking. If anybody here has ever tried to cook a steak, especially, or meat on, say, the barbecue, if you turn up your barbecue to like full heat and you put a nice thick juicy steak on there, then what will you get? You get a steak that is charred on the outside and raw on the inside. So there's certain times, if you want to cook it thoroughly or completely, it just takes a certain length of time. So we're trying to find the optimal point. That's the goal. Don't worry too much about indirect costs. They can be costs such as overhead, such as in this case of a school, the indirect costs would be costs that are related to, and they're related to overhead. You can see supervision, administration, etc. Heating for the room, direct costs would be example of. The direct labor, any materials that are consumed in a regular classroom, either chalk or felt or things along that line, or paper if you have a paper test. So in this particular case, You find the direct and the indirect costs, and you total them. Fairly straightforward. Which alternatives to shorten, or which activities to shorten? As I mentioned, the cost-time relationship is not linear in some ways. It is linear for an individual activity, but it is non-linear when the first unit is $100 a day, the second unit is 125, the next unit is 160. It gets more and more expensive, diminishing marginal returns. You need to crash. The slope is based on the time unit. It's actually negative. And project management people know that. There's no possibility of a positive number, because what you have is an increasing cost would be your numerator, the top part of the formula, and a reduction in time, would be your denominator. So you're always going to have a negative on the bottom. So you always have a negative answer. So, and you have a range, what I call crashability. So if its normal time is 7 days, but you can do it in as little as 3, the crashability is 3 days. You can compress it 1 day, 2 days, or 3 from 7 to 4, but you cannot, no matter how much money you have, you cannot have it done in less than 4 days. And you can see, you assume that it's linear. Here's the formula. Now, they have done it so you get a positive number. Most project management textbooks do it where the crash time minus the normal time. Either way, it's simply the difference in cost over the difference in time. And even though it is, as you can see, the slope is negative. So if you want to be really, really picky, this slide is wrong. It's minus $80. But everybody knows that, because you're going from, in this case, 10 units of time to 5 units of time, but your cost is going from $400 to $800. So you spend $400 additional dollars to reduce it by 5 time units. In other words, $80 per unit of time. It is assumed that it's linear, that it's $80 for day 1, $80 for day 2, $80 for day 3, if it's that particular activity. But if you go from activity A, which is $80, activity B, as long as it's on the critical path, we'll talk about that more in a moment, would be $80 or higher. It would be $92. But B would always be $92. So in this particular case, you are given the maximum crash time, the normal time, which is calculated by 3 days is normal, 2 days is the shortest it can be. It costs you an extra $20 to go from 50 to 70. Activity B goes from 6 to 4, so that's a crash time of 2. And the costs go from 80 to 160, so that is 80, and then the 80 divided by 2 gives you the slope of 40. So take the normal time, subtract the crash time. That will give you your denominator. And then take the crash cost minus the normal cost. That will give you the top part, the numerator of the equation or formula. And then you divide. So just one more time. For C, it's 1 day, and the costs go up by $30. So technically, it's 30 divided by 1, which is 30. So you can do the math on the rest. 11 minus 7 for D is 4, and the costs go up $100. And on a per day basis, that would be $25. Now, some, like G, there is no slope. You can't make it shorter, no matter how much money you have. And stretching it out does not save you money. So you have a horizontal line and a vertical line, no slope. So in this particular case, you've got the direct and the indirect costs. You change the activities and shorten them, so your costs go up. Now you have to be careful to select items that are only on the critical path. And I'll go through some examples from the book that would perhaps make it more clear than some of these diagrams. But if you go from 23 days to 22 days, assuming these are in days, your costs go from 495 to 525. And you're going to select, first of all, D, because D is less expensive at $25 than F, which is $30. And you will use D until it is completely used up. So to shorten the project from 24 days to 21 is 3 days, and you would use C, D, and E to change those by reducing them. So then you have this total cost. And again, I will go through some examples from your textbook, which might make this a little bit more clear. At 25 days, it's going to cost you $850. At 24 days, $820. At 23 days, $795. At 22 days, $775. At 21 days, $810. For our examples, though, it will typically be the longest time, which is this is $25, and the crashing will cause the cost to go up. Because if you could, a cost benefit analysis, if you spend $5 as a cost, but you can save 10, you would do that. So it's already going to be at the optimal point. What you're trying to do is simply reduce the duration, the time. So and those are the kind of questions I'm going to give you. It's already optimal, but you want to make it shorter. So you could reduce the scope. Like maybe you're going to university and you want to double major on something, but it's just going to cost you too much money. So you might just take a single major, things along that line. Or rather than going on a 2-week trip, you go on a 10-day trip or a 7-day trip. So those are the topics from chapter number 9. And I strongly encourage you to watch some of the examples that I will go through from your textbook.